Okay, welcome back. Today I'm very excited to continue discussing about our velocity model building algorithm referred to as FWIME. So the first part was about how we formulated and designed our objective function. And today we're going to explain the scheme we developed to actually minimize or optimize this cost function in order to solve our optimization problem. And we refer to this scheme as model space multiscale approach. Okay, so this is our FWME main storyline. The first part, theory and design, was the topic of the last set of videos. And the second part, which we will present today, focuses on model space multiscale approach. And in the last part, we will present our results on benchmark numerical tests. To refresh our memory, let's recap the main takeaways from the last part, theory and design. Okay, so recall the FWME objective function shown here. And note that for clarity purposes, I renamed p tilde star by p tilde opt, which stands for optimal. This is done to make clear that this star did not symbolize adjointness, but instead that p tilde optimal stems from an optimization process. The objective function is composed of two terms. First, a data fitting term, which is a modified FWI objective function, and second, a wave equation MVA term. In the data fitting term, we add a data correcting term to ensure phase alignment between observed and predicted data. And this data correcting term is obtained by applying the extended Born modeling operator B tilde to an extended perturbation P tilde optimal. We saw that P tilde optimal, or P tilde opt, is computed iteratively every time our velocity model MI changes. And such computation is referred to as the variable projection step in FWIME. We also saw that p tilde opt possesses similar features as extended images, which can provide valuable information about the accuracy of our velocity model. Our modified and invertible DSO operator plays a key role in the MVA term. By enhancing the energy present in p tilde opt, it contributes in guiding the FWME towards the global minimum. Finally, the trade-off parameter epsilon balances the relative contribution of the two terms, and this parameter is selected once and for all at the beginning of the inversion process. Okay, so now that we've built a nice objective function, let's see how we minimize it. We first go through the steps for conducting conventional gradient descent minimization. We then explain how we incorporate our new multiscale approach to FWME, and we apply our technique on simple numerical examples. In today's video, you're going to see plenty of simple but exciting numerical examples in order to show you how FWME can invert different wave types without any modification of the algorithm. For the sake of this presentation, each numerical example will focus only on one type of wave, transmitted, reflected, and diving waves. However, in the next video, you will see how these wave types can be simultaneously inverted without having to select or filter any components of the observed data. And this will demonstrate the power of our method and its simplicity of execution. Okay, so today we will decompose our presentation into three parts. First, we're going to show you how we optimize our cost function, and for this, we're going to gain better insight on the structure of the FWME gradient. Then, we will illustrate our scheme by successfully inverting purely transmitted waves using the same borehole experiment we showed in the previous video. And finally, we will show the limitation of our formulation on an additional numerical example. In fact, these limitations led us to design a different inversion scheme that we call model space multiscale. Unlike conventional FWI, we simultaneously invert the full data bandwidth, which may include all wave types, and then we conduct a multiscale approach, but directly in the model wave number domain by parametrizing our velocity model on spline grids. And finally, we will revisit the examples that failed in the first part and show that indeed, if we combine FWME with our model space multiscale workflow, we can successfully invert all wave types. For the optimization, we will begin by analyzing the properties of our gradient. As expected, we will see that it is the sum of an FWI gradient and an MVA gradient stemming from the differentiation of the data correcting term. The MVA gradient is computed with an operator called the tomographic operator, which is a modified version of a very well-known operator in the reflection FWI or RFWI community. Then we apply FWME on two numerical examples. We successfully invert transmitted waves by revisiting the borehole experiment we showed in the first video. Then we'll see that the current FWME formulation is not robust enough on a simple reflection example. And then we'll conclude on the need to incorporate a new tool to mitigate this issue. And let us now investigate the gradient. Recall the conventional FWI objective function, which is the L2 norm squared of the data residuals. And we refer to the data residuals as RD. And we know that the FWI gradient can be expressed as the mapping of the data residuals into the model space by the adjoint of the Jacobian operator of F, also called B adjoint, or B star. Indeed, B star is also known as the migration operator. In FWME, we compute the gradient in a similar fashion, except that now our data residuals also include our data correcting term B tilde opt. And we can show that the gradient is composed of two terms. First, a kinematically similar term as the conventional FWI gradient, but with a modified adjoint source RD that includes the data correcting term. We refer to this term as the Born gradient. The second term arises from the differentiation of the data correcting term with respect to the velocity model. It is kinematically similar to the gradient obtained from wave equation MVA techniques. You will see today that this term is essential to recover the missing low wave number components of the velocity model at early stages of the optimization process. It is computed by applying the adjoint of the tomographic operator T to the FWME data residuals. And this operator T is crucial for the success of FWME, and we will therefore spend some time to analyze it further and understand why its properties are useful for our method. And we refer to this gradient as the tomographic gradient. Let's analyze now this tomographic operator. So here we begin with a less intuitive way to see T. But mathematically, the tomographic operator T is the partial derivative or the Jacobian of the data correcting term with respect to the velocity model Mi, while keeping P tilde optimal, or the reflectivity, constant. So now let's see in plain English what this really means. So to simplify things, consider the not extended case. So B is simply the conventional Born modeling operator, and P is a non-extended image or a reflectivity model of the subsurface. Notice that the term BPopt lives in the data space and is obtained by demigrating the reflectivity Popt. We say that BPopt is some Born data. Here, note that the demigration is performed with a background velocity model Mi. Therefore, the tomographic operator tells you how this demigrated data change when we perturb the velocity model Mi using the same reflectivity. The action of T can be summarized with a dimensional analysis. We begin with the velocity perturbation delta V that lives in the model space. Then, T is going to map this perturbation into some Born model data which lives in the data space. Additionally, T uses an extended reflectivity or extended perturbation assumed known and fixed throughout the process. In an analogous manner, T star, or the adjoint of T, is going to map Born data into velocity model updates. And if you remember from the previous slides, T star, T adjoint, is the mapping used to compute the FWME tomographic gradient. Before we try to understand the mechanism behind T star, we will try to give you an intuitive understanding of how T operates on a simple cartoon. And also, for the sake of this explanation, we're going to restrict ourselves to the non-extended case, which is conceptually similar to the extended one. However, in FWME, as we explained in our previous video, all our variables and operators are extended. So we consider a cross-section of a homogeneous Earth whose seismic velocity value Mi is known. Assume also that we're given the exact location of some reflectivity model Popt. Then we demigrate this reflectivity using the velocity value of the homogeneous Earth. And then we record at the surface the demigrated data Bpopt. As previously mentioned, we call this demigrated data Born data, and we abbreviate it by dborn. Now let's consider an analogous experiment, but here we perturb the Earth by adding a velocity anomaly delta Mi. We repeat the same process and we record the modified Born data at the surface, stemming from the demigration of the same reflectivity Popt, but this time with a perturbed background velocity model. And we call this new born data dborn of mi plus delta mi. And now I hope that you have a better intuition on the physical meaning of the operator t. Given some fixed reflectivity p opt, it is the derivative of the demigrated data or the born data when we perturb the velocity model used for the demigration. After all that, t may still seem obscure to you. However, its adjoint t star is a well-known operator used by the reflection FWI or RFWI community. However, in RFWI, a non-extended perturbation or reflectivity is used. And to give you a hint of what we're going to see next, this is one of the operators responsible for what people call the rabbit ears velocity updates. Following the same philosophy as in the cartoon illustration, we now consider the following numerical example. We have a homogeneous Earth and a background velocity model set to 2 km per second. We also consider a surface acquisition setting where we place multiple sources and receivers. And finally, we're also given a horizontal reflector shown in the red line at a depth of 2.4 kilometers, which will play the role of our reflectivity. We begin by generating born data by demigrating with the velocity v0, and we obtain d born 0. Then we add a Gaussian velocity perturbation delta v whose maximum value reaches 0.5 kilometers per second. And we recompute our new born data dborn delta v. And finally, we compute the difference between the two born data delta b born. Now here, if we assume that the reflectivity is given, we know the position of the reflector, the only unknown we may want to recover is the velocity perturbation delta v. And for that, we're going to apply t star to the born data difference delta d born. This panel shows the application of t star to delta d born, but computed for a single shot located at x equals 12 kilometers, using all available receivers at the surface. This image is indeed familiar as we can recognize the well-known rabbit ears tomographic update. Let me now switch a few times between the two images to show you how the update path coincides with the position of the velocity anomaly. Finally, this panel shows the result of applying t adjoint to the born data difference delta d born after stacking the contribution of all shots. The anomaly is well captured, but the update lacks vertical resolution. We can observe that indeed no updates are present below the position of the horizontal reflector. Again here, I will flip back and forth between this panel and the true anomaly to show you how well the update managed to capture the velocity perturbation. Here, I want to highlight the fact that we're using reflection data to produce a low wave number or tomographic velocity update, which is the fundamental principle behind both our FWI and FWIME. The main difference, however, is that we use an extended reflectivity or an extended perturbation. So on one hand, yes, it is definitely more computationally intensive. However, we will show you soon that this additional degree of freedom coming from this extended perturbation allows this tomographic operator to provide the correct velocity updates even if the perturbation falls outside of the linearization approximation, which is not the case for RFWI. In other words, if your delta V is too large and you are not using an extended reflectivity, you will likely end up with an incorrect velocity update. I want to make it clear that FWIME is not just some slightly modified version of FWI or RFWI that would converge faster to the same minimum. Here we are tackling a first-order problem. By this we mean that we're building a technique able to converge to an accurate solution when more conventional methods such as FWI or even RFWI will get trapped into non-useful local minima. But indeed this comes at a higher computational price. So to summarize this first section, we said that our gradient is composed of a born component that shares similar features with the FWI gradient, and the tomographic component that is key to update the crucial missing low wave number components at early stages of the inversion process. To come back to the plot shown in our first video, we can now better understand our claim that FWIME combines both MVA and FWI techniques into one single workflow. And now we're going to test our algorithm on some numerical examples. In the first numerical test, we revisit the borehole example introduced in the last video, and we successfully invert purely transmitted waves. To refresh your memory on the experiment setup, we place two vertical boreholes separated by 1 kilometer. We place sources on the left boreholes and receivers on the right one. The true velocity is homogeneous and set to 2.5 kilometers per second. And we use a source with energy strictly limited to the 9 to 35 Hz frequency range. And we make no prior assumption on the model, and we invert for approximately 10,000 unknown parameters. Indeed, the observed data is composed of a single event generated by a purely transmitted wave. And finally, the initial velocity model is homogeneous and set to 2 kilometers per second. First, we're going to check that conventional FWI has no chance of converging to the global minimum in such a setup. The panel on the left shows one representative shot gather from the observed data generated by a source placed at a depth of 0.5 kilometers. The middle panel shows the predicted data computed with the initial velocity model that is too slow. And the right panel is the difference between the observed and the predicted data. As expected, we clearly see that the two events are cycle skipped due to the inaccuracy of the initial model. We conduct conventional FWI until convergence, and the middle panel shows the predicted data at the last iteration of this workflow. As expected, FWI converged to a local minimum and the data are still cycle skipped, as we can see from the right panel. The velocity value was not increased enough and FWI is unable to correctly match the observed data. And now we conduct 100 iterations of FWME on the exact same problem. And here I'm going to show you a sequence of 7 slides. Each slide will display the observed data on the left, the predicted data in the middle, and the data difference on the right at a given FWME iteration. Indeed, we want the middle panel to resemble the left panel as closely as possible, and the right panel to vanish. Also, note that all panels are displayed with the same grayscale. Now at iteration 15, we can clearly see that the predicted data begins to align with the observed data. And from that point on, the data are not cycle skipped anymore, and the inversion can converge towards the global solution. Finally, at the last iteration, the predicted data matches the observed data perfectly, and the data difference has vanished. And now we're going to analyze the sequence from a different angle. This plot shows the total FWME cost function as a function of iteration number. It successfully converges to the global solution after approximately 100 iterations of FWME. The red curve in this plot corresponds to the value of the conventional FWI objective function evaluated at each FWME inverted model. It is not the result of an inversion process, which is why we label it by FWI in quotes. As expected, it is not monotonically decreasing, which illustrates that the FWME algorithm has successfully created an alternate descent path towards the global minimum that could not have been taken by conventional FWI. And now we're going to travel along this red curve and try to see if we can make sense of its shape by observing again the difference between the observed and predicted data shown here on the right panel. Note that this panel is the same as the right panel showed in the previous sequence of slides. After 10 iterations, we can see that the prediction gets closer to the observed data. After 15 iterations, the two events begin to align. As they do so, they constructively interfere, resulting in an increase of the L2 norm of their difference. This is confirmed by the fact that the FWI objective function, the red curve, reaches its maximum value at that iteration. This perfectly illustrates the cycle skipping phenomenon inherent to FWI, and its inadequate way of measuring the error in the data space when the initial model is too inaccurate. Here we know that our predicted data and our model are getting more accurate, but from an FWI measurement standpoint, we're heading towards the wrong direction. However, FWIME is telling you the right information, as its objective function value is still decreasing. This specific point should be further analyzed. If you look closely, you can observe the presence of a sharp discontinuity in the rate of convergence in the FWIME objective function shown in the blue curve. Intuitively, this is the point where our inversion is able to climb over and reach the global basin of attraction of FWI. Note that here, nothing was tuned or modified during the inversion process. We just let the inversion proceed without adjusting any parameter. Okay, let's make a small digression to investigate this behavior a little bit further, and let's just focus on the FWIME objective function for now. The flatness of the FWIME curve at iteration 15 illustrates that our objective function kind of struggles a little bit to overcome this FWI bump. Moreover, this inversion was conducted with a constant trade-off parameter epsilon. Let's call it epsilon 1. Now if we perform the same FWIME inversion, but this time with a higher constant epsilon value, say epsilon 2 equals 5 times epsilon 1, the new FWIME convergence curve is much more convex, as we can see from the pink curve shown in the plot. And this also illustrates the importance of this trade-off parameter in our inversion. And though we do not have an automatic way to select it yet, we will explain how we can estimate it in the next video. And once our inversion has passed this tipping point, it converges more rapidly to the global minimum. We can plot the inversion results by comparing the average of the inverted velocities with conventional FWI in red and with FWIME in blue. We chose this model metric because of the inherent uncertainty in the conventional travel time tomography problem, especially with such an unconstrained problem as this one. Finally, we can clearly see that FWIME converges to the optimal solution, whereas FWI is trapped in a local minimum. Now that we have successfully inverted purely transmitted waves, we're going to test FWIME on reflection data. We use a similar model as the one proposed by Mora in 1985, and we consider a model composed of two horizontal layers with an interface at a depth of 1.1 kilometer. The velocity v0 of the top layer is set to 2.7 kilometers per second, and we generate an acoustic noise-free dataset with sources and receivers at the surface. We use a seismic source with energy contained within the 20 to 50 Hz range. Our maximum acquisition offset is 4 kilometers, and the dataset is dominated by reflections. In the top layer, we perturb the background by 20% by adding a circular low-value velocity anomaly of 2.2 kilometers per second. This panel shows the true velocity model that we wish to recover. Our initial model is homogeneous and set to the top layer velocity value 2.7 kilometers per second. We conduct a data space multiscale FWI using 4 frequency bands, and the final result is shown here. We can observe that the solution becomes quite inaccurate in the vicinity of the anomaly, especially in the zone underneath the anomaly and above the interface. And now we're going to try to do better with FWIME. Here we're going to guide you through the first step of FWIME. We begin by computing the difference between our observed data, f of m true, and our initially predicted data, f of m0. And the difference is shown here in the middle panel. We can identify some events corresponding to the reflections from the top and the bottom of the anomaly, as well as from the horizontal interface. We can also see some triplications due to the distortion of the wavefield as it passes through the low velocity anomaly. And the next step is to compute the optimal extended perturbation, p tilde opt, by conducting the variable projection step. For this example, we use horizontal subsurface offset for the extension of p tilde opt, and we extract a common image gather at x equals 2 kilometers. Here we're going to analyze the origin of the events present in the data difference. Then we examine where these events map in the extended space of p tilde opt through this variable projection step. The first event we can identify is generated by the reflection from the top of the anomaly and is shown in the pink arrow in the middle panel. This event is then mapped via the variable projection step to a well-focused event in the extended space of p tilde opt, as we can see on the common image gather shown in the right panel. This was expected because the velocity down to that depth is accurate. As we move deeper into the section, we can see that the events corresponding to the bottom anomaly, showed in green, and the interface, showed in yellow, are less focused since the velocity errors begin to accumulate. Moreover, on the right panel, we can see that the event corresponding to the reflection from the horizontal interface right underneath the anomaly, shown in the yellow arrow, not only lacks focusing, but also begins to lose coherency. And this is the kind of effect you may expect in the presence of complex overburdens. So we can now compute the first search direction. As we explained in the previous section, it is composed of the Born component, shown here on the top left panel of the screen, and the tomographic component, displayed on the top right panel. And the total search direction is the sum of the Born and the tomographic components. By examining the first row, we can see that the Born search direction is similar to what we would expect for the first FWI1. And the tomographic search direction, however, seems to fill the anomaly and better capture the missing low wave number components of the true model. These two figures show the amplitude spectra of the spatial Fourier transforms of the initial FWME Born search direction on the left panel and the initial search direction of conventional FWI on the right panel. As expected, the two seem to recover the same wave number components of the model. And if we compare now the FWME Born search direction with the FWME tomographic search direction, we can clearly see the benefit of this additional component as it allows us to recover the low wave number components that the Born cannot. The total FWME first search direction is the sum of the two panels on the first row and is shown on the bottom left panel of the screen. And by comparing this panel with the ideal update, we can see that the first search direction seems promising. Unfortunately, despite many attempts, and by this I mean by sampling different values of the trade-off parameter epsilon, we were not able to recover an ideal solution. And here we summarize our results. We can see that the FWME model slightly improves the FWI result, but is not really able to recover a useful solution. So before we move on and explain how we can make FWIME more robust, we're going to examine one last pathological but very informative numerical example. We consider a surface acquisition setting, and the true model, shown here in this figure, is a laterally invariant linear V of z. Its profile is shown in the blue curve on the plot. We also place a sharp interface at a depth of 2.1 km to generate a reflection. Our initial model is also a linear V of z, whose profile is shown by the red curve on the right plot. Moreover, it does not contain any interface. We use a source whose energy is limited to the 9 to 18 Hz window, and we mute all the events in the data beyond 3.5 km, such that our dataset is solely composed of reflections, as you will see in the next slides. In a similar fashion as we did for the previous examples, we're going to go through the first step of FWME. We compute the initial data difference, D observed, or f of m true, minus f of m0. Remember, for this example, we are only interested in working with reflections, so we muted the signal at larger offsets. In the middle panel, we can see two reflection events in the initial data difference. The earlier one, shown by the pink arrows, comes from the fact that the initial model has an incorrect velocity gradient. The latest one, shown by the green arrows, is due to the absence of the interface in the initial model. And now we use the variable projection step and we can compute the initial p tilde opt. And for this example, we're going to use horizontal subsurface offset. And we examine a common image gather at a horizontal position of x equals 4 km from this p tilde opt. On the right panel, we can see that the energy of the event coming from the deepest reflection dominates the common image gather. As expected, this event is not well focused and shows a frowning move out, indicating that the value of the initial velocity is too low. Okay, and now the next step is to compute the initial search direction. As a reference, this is the normalized ideal search direction, the normalized difference between the true and the initial models. This figure shows the initial search direction from conventional FWI. Note here that we applied a mask to the gradient to avoid updating the shallow part of the model near the sources and receivers. Indeed, since the initial velocity is too low, the event coming from the interface is mapped at an incorrect shallow position, as we can see in the figure. In the test not shown here, we observed that conventional FWI is not able to converge to an accurate solution. Not surprisingly, the first FWME-borne search direction is kinematically quite similar to the FWI one, and the interface is also wrongly positioned. The tomographic search direction looks much more promising than the borne one, as it seems to correctly update the low wave number component, and it also seems to be guiding the inversion towards the right direction. One interesting observation is that it also seems to update parts of the model underneath the position of the true interface. First, this is not a bug or a computational error, and although we do not have time to thoroughly explain this phenomenon, this is mainly due to the fact that the perturbation we use is extended. And the mapping of this event in p tilde opt displays a frowning move out in the extended axis, thereby spreading energy in deeper regions of p tilde opt. Now, if you're interested in understanding this feature in more details, do not hesitate to contact us. Now, when we sum the borne and tomographic search direction, we obtain the first total FWME search direction shown in this figure. And unfortunately, even though the tomographic search direction seemed to be very accurate and very promising, the amplitude of the borne search direction dominates. We summarize the different components of our first FWME search direction. Here, the borne, tomographic, and total search directions are displayed on the same color scale. And unfortunately for us, FWME wants to listen more to the borne, which we know is wrong, than to the tomographic update. So from this example, we can see that we're now facing a major challenge. We have two components, one that seems useful, the tomographic one, and one that seems to guide our inversion to a local minimum, the borne. The tomographic update is crucial to us as we know that recovering the low wave number components from the start is necessary to converge to an accurate solution. The problem is that the amplitude of the tomographic component is too weak with respect to the borne. So one way to fix this is that you could manually adjust the two scales and boost the amplitude of the tomographic update, but that would create two main issues. First, it would be very user intensive, which would defeat the purpose of us trying to make this algorithm mathematically sound, clean, and automatic. And second, how do you know how to adjust the relative weight for future iterations? This is clearly not viable, so we need to find an alternate solution, which is indeed what we will introduce in the second half of this video. Okay, let's recap what we have learned in the first half of today's video. First, we saw that the FWME gradient is composed of two terms, a borne term similar to FWI, and then a tomographic term similar to a wave equation MVA gradient. And this tomographic term is very good at recovering the missing low wave numbers of the velocity model, even just with the reflected events. Then we tested FWME on three examples. We successfully inverted transmitted waves in the borehole experiment introduced in the previous video. However, we saw that for the Mora example and the V of Z model, we failed at converging to the global solution. However, we saw that things are not completely hopeless. By examining the different components of our gradient, we noticed that at the first iteration, the tomographic update seems to guide us towards the right direction, but its amplitude is overwhelmed by the borne. So we want to be able to reconstruct or recover the low wave number components first. Therefore, we need to find a way to automatically adjust the relative weights of the FWME gradient components. And as we mentioned at the beginning of the video, Ettore and I have developed a strategy called model space multiscale approach that achieves this goal. Okay, let's go back to our main storyline to see where we stand now. So we're currently in part 2, optimization with model space multiscale, and we just finished learning about how we optimize FWME. In the next section, we'll learn about our model space multiscale approach.